Hello, everybody. My name is Shoroy Viducci. I'm here to show off the Zeal ISA, or rather, the proposal of it. This is for my thesis, and let's begin. So, what does an ISA stand for? ISA stands for Instruction Set Architecture. That means what instructions a CPU can run, what are the instruction types, what's the encoding of those instructions, and depending on who you ask, it can include some other details. But let's just focus on these first three, because that's what I care about. What ISAs are there? Well, the big three are x86, ARM, and RISC-V. x86 is the one you usually see in your desktops, your servers, your laptops, and some of those good old mini PCs. Well, ARM is trying to do everything. They're trying to be your toaster. They're trying to be your smart fridge. They're trying to be your cell phone. And everything x86 is trying to do. They got their tentacles over everything. They're heck of evil. They're very evil. And RISC-V, well, to be blunt, they've got the same ambitions as ARM, but they're not there yet. One of their most recent gains was being included in a whole bunch of Seagate hard drives. And allegedly, NVIDIA GPUs. That's a bit more recent, the NVIDIA GPU one. The RISC-V dudes themselves don't even know if that was true or not. They just saw, oh shoot, they're interested. And they saw NVIDIA said a whole bunch of RISC-V microcontrollers started getting shipped by them. And something, they don't even know what. But anyways, what are they used for? What is an ISA meant to do? What is it supposed to be used for? Well, I'm glad you asked. See, you can design a chip to do exactly one thing and nothing else, and sell that, and that might be okay for some people, but most people want chips that are programmable chips. And in order for a chip to be programmable, well, you gotta have some instructions. The ISA lays out the machine code and the assembly code. You turn that assembly code into the machine code, and yeah, the CPU will run the machine code. It was pretty normal for quite a while, a few decades even, for everything pretty much to be written in assembly. Now, not everyone was doing that, but a lot of people were doing that. Your Unix, your video games, your operating systems, everything. You could have done it in assembly for different chips. And right here, okay, I'm gonna drop the Southern Act for a little bit. So I was losing a bit of focus. So here's an example of both the machine code and the assembly. We got two architectures. We got MIPS on one side, RISC-V on the other. And this is for an add instruction. Right here, they put the opcode. That's the operation code. That's like what instruction it exactly is. This one specifically for add. There's a special field here. I don't quite remember what it was. I don't care. I'm not exactly the biggest MIPS fan. RD and RD is a destination register. RS and RT, those are source registers, as in, well, you read it like this. Okay, I'm going to add source register and the other source register. I don't know why they call it RT, but sure, maybe it's because T comes after S. Anyways, RS plus RT goes into RD. You read it like that. That's a bit weird. That's how it is. And then in the RISC-V land, it's pretty much the same thing, except they just call it RS1 and RS2. That's your destination. They have an opcode field, and instead of a bunch of zeros here which do nothing, they have a function 3 field and a function 7 field. This function 7 is probably like the special field over here. I don't know what that function 3 field does. Oh, that's okay. Let me think. Okay, yeah, that just defines what type of arithmetic instruction it's doing. Again, I'm just trying to show off an example. Your assembly turns into machine code, as I said, and I just want to show that. Anyways. Um, I'm not showing this off to a professor because I already did that, so haha, I don't have to worry about being on a timer anymore. I can be a bit more relaxed. But anyways, on to our problem. Nobody programs an assembly anymore, and I think there's three reasons why. One, modern ISAs are a mess. Two, there's too much abstraction with everything. And three, our culture has been ruined by various villains and such. And so assembly isn't as hot as it used to. Though certain projects like FFmpeg obviously have a lot of inline assembly, and that's awesome. But anyways, reason two. Well, we'll start with the reasons. Go into the detail. Modern ISAs are a mess. ARM and RISC-V are trying to do literally everything, and this is literally impacting their design. Like ARM's got the 32-bit instructions, but also has to be able to run its thumb instructions, 16-bit instructions, and it's got like the microcontroller versions of stuff and all sorts of things. And it's the same story with RISC-V. They've got both the 32-bit instruction versions themselves and the 16-bit instructions and blah blah blah. You got to be able to mix and match. At least with ARM, I know you got to do that. And x86, they have to be able to be backwards compatible with the original Intel 8086, all the software that was written for that, all the way up till now. And to be fair, x86 also wants to do a lot of things. And well, look, I'm not exactly saying any of these designs are terrible. I don't know better than them. They know more than me. They're quite performant, and as much as I hate ARM, they do ship products and people are buying them. But I'm not here to focus. This thesis is not here to focus on performance. This thesis is to focus on readability and education and all that good stuff. We want a pleasant experience for the programmer. And stuff like variable length instructions or whatever the heck this is, where you got like, let's see, 1, 2, 3, 4, 5, 6, 7, 8. That's 8-bit fields. That's crazy. You want people to read that line by line? Heck no, that's not going to happen. And x86 is unfortunately worse, where you can have like not just 32-bit long instructions, you can have like 8-byte long or 2-byte long. Or I say byte, as in I literally mean byte, not bit. So when I say 2-byte, I mean 16-bit. When I say 8-byte, I mean 64-bit. I think it can be even longer than 8-byte. It can be maybe 16 bytes, but I haven't been counting. Anyways, so abstraction. Well, let's say you want to be a cool assembly dude, but you're programming on Windows or Linux. Well, that sucks. You still have to deal with the operating system APIs, and you can't just directly poke an area in memory to do something like draw a pixel or whatever. You have to still follow the operating system's rules. Besides that, on the high end, the reason why no one cares about low-level anymore is because they keep pushing us to go program in the higher-level languages. We got our interpreters and virtual machines and all type of crap. Java has its virtual machine. I make fun of it and say it's like as slow as the Charles Babbage analytical engine. And I also imply by saying that it doesn't even work many of the times. It doesn't quite work right. And then, yeah, that's Python interpreter. That sucks. Object-oriented sucks. I don't like any of this stuff. I like up to here. Pascal and C and Fortran, that's all cool. I mean, I wouldn't personally program in Fortran, but I love Pascal. I like C. I like Turbo C++, not specifically for the C++, but it's Turbo C++ wasn't even around when the 1985, I mean 19, what's it called? The 1998 standard for C++. It was just C with classes. It was mostly still C programming. Anyways, and yeah. I'll pretend I still want to I don't want to take too much time on the slide. This is going to be like 30 minutes probably. Now, as for ruined tech culture, I already gone over that some of that because the related reasons. Like these universities, they say, "Oh, we're going to teach you to be a software engineer," and then they just tell you to do web development, or like you got companies like Facebook. They're like, "Yeah, we were already being stupid and lazy with our WhatsApp." With our WhatsApp desktop application when we were using UWP instead of just the native Win32 API. Some people still mistakenly called that as a desktop, I mean like a native desktop, which I mean, sure, kind of, a little bit. It's not quite the web slop garbage, but UWP, as far as I understand, was supposed to you can get that running on like an Xbox or something, and like or Microsoft phones. Um, And then when they switched to making a web app version, they went from 100 to 300 megabytes to 2 gigabytes. Wow, that's a 10. That's more than a 10 times increase, like 20 times increase. What you doing, man? Um. So yeah, like hardware engineers, they're always told go make it faster. They talking. I didn't mention this when I was telling about to my professor, but they're all because I forgot and I didn't want to make this take too long. I was telling. I was thinking about how oh, Intel has the meltdown in Spectre because of the way they do out of order execution or whatever. I don't know, some microarchitectural thing. And then no one ever asked, geez, why do they want to go through that type of trouble to get squeeze more performance? And well, maybe it's because your software keeps getting more bloated. Did you ever think about that? No, you didn't. This is your fault. I'm pointing the finger at the software people. But anyways, the related work. So I'm supposed to tell these college dudes that I need what my articles were, and they for some reason they say put the related work as like the middle, as in the third chapter of the presentation, which is right now. Sure, here's 23 of them. I'm not going to cover all 23. I'll cover some of the highlights. So, Alabama A&M University. Well. These guys are really cool. Whoever was working on this, I mean, I can look it up, but you can look it up even. These are the title of those IEEE approved articles. Alabama A&M symmetric overload and minimum set architecture. Minimal set architecture. This really is a minimal architecture. They really mean it. Unlike ARM's reduce R and RISC, supposed to be reduce instruction. Haha. Well, it wasn't very. ARM isn't really that reduced now. They really mean it though here. The minimal and then their successor. But that's not why I'm saying it's cool. I'm saying it's cool not just because it's minimal, but because when you're trying to read the assembly language for it, it's easy. And when we're trying to read the machine code for it, it's not too bad. And same thing here when they added more instructions, made it more developed, and they go from 2 instruction types and 4 encodings to just 1 instruction type with probably like I forgot how many probably let's say four encodings. Oh, that's great. I remember it was pretty simple. I liked what I saw. So maybe I can take inspiration for this, even if I don't copy any of their work. It was food to chew on. When I say copy, I mean I would obviously reference it, but I mean like yeah, I don't wanna step on their game and say I did it. No, these guys deserve all their credit they can get. Oh yeah, the main problem with this, if I had to critique it, isn't that the design is terrible or anything like that. Great design, love it. They compare it to Z80, 6502, Intel 8085, RISC-V, all that good stuff. Problem is, they didn't make an FPGA implementation, so all we see is the simulation results, as far as I know. That's great, but um, you know, real world results are important. And FPGA is as close as any students can get to real world because we're not going to go up to Taiwan's TSMC and say, hey man, can you print out our chip? It's going to be real awesome and stuff. We don't have millions of dollars to throw around like that. Sorry. And then another ISA focused example, that's how I'm dividing. There's like 3 sections of this related work stuff. One first section is going to be the ISA stuff we're going to think about. We got fast multiple precision integer division using Intel AVS 512. and doing that instead of using regular floats or regular IEEE floats. Why? Because if you need more precision and you don't support something beyond, let's say, a double float, double precision float, you don't have like the hardware for it, you can't just combine two double precision floats and come up with quad precision. It doesn't work like that. I wish it did, but it doesn't. But with integers, you can do that. And that's the whole point of what this guy was trying to do with AVX512. He got it to work, and he got it to work faster than the GNU multiple precision arithmetic library does, which I'm assuming that's also either integer floats or integer based, like, I shouldn't say integer floats, I should say fixed precision. When you're doing decimal math with integers, it's probably fixed precision. When you do it with floats, it's floats. Haha. Um, yeah, I don't remember if this GNU multiple thingy is using software emulated floats or it's using integers combined together. Probably integers because otherwise it would be way slower than, I mean, the AVX5 tool would be way faster than just 25 to 35, I bet. But yeah, this was cool, and this is why I want to have 128-bit registers by default. So I said, okay, and you know what? Maybe not even bother with SIMD. You want high precision decimal math? Just use a 128-bit register, and you can use it like a regular register. Do the set fixed point math, and that'll be very easy for you. If you need more precision, you can just combine the registers or something like that. I haven't quite figured out that part out yet. Uh, Now let's think about the hardware a little bit. I have to do that. Here's a couple articles. One of them is talking about I/O address space and x86, and another one is talking about direct memory operations. Well, you see, those ARM dudes and those RISC-V. I'm not going to talk about the hardware I/O space stuff too much. I'm going to talk about the direct memory operands. Well, look, all those ARM dudes and those RISC dudes and stuff, they say, well, you shouldn't be doing direct operations with memory. You should load it into a register first and then do the operations with the registers. And then this guy says, okay, that's great, but you see in my GPU, with a GPU, sometimes you're going to get, at the GPU at least, you're going to get some cases where you're reading values and then tossing them away immediately. So that whole process of you loading into a register file and then doing it in a separate instruction, that's lame. How about we just directly operate on memory? And he says he got he had say, oh shoot, well, he didn't, I don't remember, he didn't give a direct quotes on how much faster it got, but he did say a significant number of values present in the register file are typically used once, contributing to more than 25% of the total register file bank conflicts on average. So there's performance loss associated with it, and if you skip that step, you can maybe even gain some performance. You just directly work with it. And here, I'm not going to talk too much about this. Long story short, I don't want my design to be stuck in simulation world or software emulation world. Hopefully, I'll be able to flash to some sort of FPGA. This is the one picture that I have is the one I want to do because I want to give Altera stuff a shot. I've been using Xilinx for most of my university. It's like, let's go Altera a shot. Why not? But maybe I'll use something else. There's another company I spotted that's even more of an underdog. They seem to have some interesting tooling. I'll go with that too. Like interesting software, I should say, to be more clear. It seems a bit faster than Intel Quartus and Xilinx. Xilinx is just, their Vivado is just turtle speed. I don't like Java. They run on that Java crap. Oh, okay, now about the system architecture. Proposed system architecture. You see, I want an easy to understand assembly language and the easiest to read machine code. I was in someone who wants to run read and understand this architecture. I want them to have an easy time writing assembly language. And should they ever need to go down to the machine code level, which whoever wants to start with this will have to do that because, well, I'm right now the only guy who is going to write anything for it. So whoever comes after me, they're going to have to read whatever I wrote. They'll have to deal with the machine code, right? Yeah, those guys, they're going to have an easy time. It's gonna be like reading from left to right. But with that said, I don't care about speed. I don't care about the quality of the implementation. I'm gonna write some single cycle CPU, and if it works, it works, and I'm gonna be real happy if it works. Um, doesn't matter if it's slow or fast. It just needs to work. Cause yeah, and then unlike RISC and a lot of architectures these days, those big three architectures these days, I'm not trying to do everything. I want this to be something like an educational one, but not as crummy as the educational architectures tend to be, while also seeing maybe pushing it as a desktop CPU architecture, like something that could fit in the 1980s, but with way more registers and RAM, all that stuff. And when a student learns, let's say something like x86 in college, they're not learning the whole thing. They learn like a tiny bit of it and they forget it. So when they can't really say to themselves, "Yeah, I learned the whole architecture." They learn a tiny bit. That's pretty much it. This case, I'll say, you know what? Let's just learn a one that can technically exist on an FPGA. And if it exists on an FPGA, then that means it's real. I can run real programs, potentially. And that would be better than learning a fake architecture or a dead architecture like MIPS or something like that, where, yeah, it's just not fun. It's just not interesting. This one, I hope to make it real enough that it'll be interesting and someone will fork my design and make it way better. Not necessarily better ISA. Well, I should say that, yeah. It can be improved. My ISA's design, even with what I'm going to do, can be improved potentially. But I'm more so worried about the quality of my Verilog implementation. My Verilog code is probably going to be garbage. But so long as it works, then someone else can say, "Oh, here's your working design, here's mine that's way better." Great. I'm happy. Thank you very much. I unironically appreciate it if that happens. Um, Now next. So, main focus of my thesis, as you can probably already tell, is the encoding. Because if I don't care about the quality of the hardware that I'm going to be implementing, why bother with all this? Well, I want to have good encoding, as I made it clear. All instructions in all fields will be byte aligned. There won't be a single bit field smaller than 8 bits. All instructions will be 96 bits long, which is crazy, but that's what we got and that's what we're going to do. And there's got no variable length. There won't be anything like 32-bit, 64-bit, 16-bit, whatever. It's all going to be 96 bits long. And there's only one type of instruction, a very important type that worries me regarding this. So it'll be making it very wasteful, but the other ones I think it's awesome. I'll show you in a bit. Why do I have it set up like this? Well, as you can see in the words below those bullets, I want it so that when you open up a Zeal program, it's a Zeal ISA, right? Zeal program. You open up the binary and you look at it in the hex editor, you're going to say, each line is 24 hex digits long, therefore I can just limit the width to 24 digits. That means each line is going to be one instruction. Ha! Now I can read it almost like I'm reading an actual program. Whereas if you read the binary for some other thing, it's either, I think with ARM and RISC-V, you can technically do that with 32-bit binaries. You're going to be reading zeros and ones instead of hexadecimal. That sucks. But at least you can say, well, every 32 bits it's probably an instruction, something like that. Kind of, but reading binary is longer and more painful. And hexadecimals is great, right? And the encodings are just all screwed up in ARM and RISC. But mine is going to be awesome. So the sorry, it just feels really good that I don't have to. This video is going to go to the public instead of presenting it, so I can give jokes like that. 2 people will watch this video, 3 people if I'm lucky. Instruction formats, or I should say, get this far. A lot of people watch the first 5 minutes and then tab out. So yeah, 5 or 6 categories: register to register, immediate to register, memory to register, register to memory, and jump. And because it's a 16-bit field, that means I can do what I just did, where each first digit is the category. A is for register to register. You already see it. I'm not repeating that. If these categories are not good enough, you can make other categories. We got 10 available slots. I could have wrote 0, 0, 0, 0, but that's not fun to look at. 1,000, 2,000, 3,000. Not literally 1,000, 2,000, 3,000, of course, because it's in hexadecimal, but you get what I mean. If you go past 4,096 options for each category, I think you should consume a lot of alcohol and start driving down a very busy highway. So you get in trouble, of course. Anyways, no, joking aside. That's because that shouldn't happen, because the whole point of this is that you should be able to fit the menu in like a couple hundred pages, a few hundred pages, not in the thousands like modern architectures are, okay? Hope you got that. Here's immediate to register. We got this copy instruction. This is like the move from x86. We read it from left to right. So move seed feed beef beef. This is some number that you can convert it to decimal to this register. And then these 2 extra zeros are, you don't need them. That's the math to see that's in this a 96-bit instruction. Or there's a jump instruction. We got branch greater than, right? So we got, I would say like E001 would just be a normal jump, and then this would these 2 would be empty, these 0 registers. But yeah, 0, that's a 0 register, as in it holds the value of 0. There's no comparison then, or these would be ignored. But anyways, yeah. In this case, it's a branch greater than, so branch greater than if register 1 is greater than register 2. That's the case. Go to this address, ABCD99999. I said too many nines, I think. Register to register. This is the one where I think it's going to be a little silly, because now we have all these zeros we don't know what to do with. My response is this craziness right here, where I said, okay, you know what? It might not work up for copying, but you know what we can do with this? We can do this. The add instruction, we do R1 plus R2, R3 plus R4, R5 plus R6, R7 plus R8, R9 plus R10, and it works out. And that's awesome. Yeah, I seriously don't know what to do with copying, though. These would just be zeros, like, once again, 0, 0. That'd be 0 register, just ignore everything after that. That's gonna be so wasteful. Unless we can still do the same thing. We can still do multiple copy operations at the same time, of course. Maybe it won't be too bad if someone figures out how to prepare them from advance, like you prepare a bunch of immediates from the beginning. I don't know. Now, this will be the biggest weakness this architecture has, unless I legalize, let's say, 48-bit instructions, and when a 48-bit happens, no, I can't do that. Experiment and evaluation plans. Once again, I don't care about the performance. It just needs to work. First milestone, can I get a single cycle design working in a simulator? Second milestone, can I get it working on an FPGA? Like, just flash it and have it run a few instructions and give a readout on some LCD or whatever. Or like some LEDs. Anything. And then, can I get a very basic operating system? Like have it read off an SD card, some program, and give me some results, whatever. And then after that, we can start working it into something like actual computer, like have the user play games on it or whatever, or get to HDMI output or something. Because the DE10 Nano has, oh, I say HDMI, this one uses VGA. Same thing. Not literally, but get video output, get some awesome video output, get some colors, graphics, demos, whatever. That's a dream, though. I don't know if I'll reach that. Worst comes to worst, I'll write a CPU emulator, like a software emulator that just executes the instructions, and I have an assembler for it. But I don't know. Then future plans. Either the best case or worst case, I'll have a programmer's manual to go with this all. And the only way I can know if I'm finished is if I make progress to begin with. So far, it's just been research and distractions. And then, as more progress is made, study other architectures and continue studying other architectures compared to Zeal. See what weaknesses Zeal has, see what strengths, even if you just consider it as educational and desktop architecture. But that's pretty much it. It's the end of the slideshow. I'm not releasing this PPTX yet anyways, but the person who is going to get it, he'll be able to see the sources I got. If you want to know, this drawing is mine. I made it like a super long time ago. I'm proud of this drawing. I love Berserk, as you can tell. Oh, and the more important thing, I did this in the Zeal OS Paint application, which I had a hand in programming, but Tom did the better rewrites. Uh, Also mine. These three are mine. This weird text, the way I write it, that's mine, that's mine, that's mine. Not these two tables, though. These two tables, I stole them, of course. This is also mine, haha. So I wanted to make it a little Zeal-themed, Zeal OS thing. Oh, yeah. That one's also mine. These are an MS Paint, of course. But yeah. Hope you enjoyed. Hope you listened. If we can get 50 views, comment below. Oh, I'm kidding. Whatever. Extra video to my YouTube channel. If you generally watched and you generally learned something, thank you very much. I'm very happy to hear that. I love to hear that. I love to see people learn. But yeah, hopefully I'll upload some more stuff. I always say that doesn't happen, but whatever.